is it that a massive cruise ship with thousands of passengers and literally tons of food, furniture, and other objects floats? Why do planes stay in the air despite the strong pull of gravity on their heavy bodies? What's counterintuitive about the answer to these questions is that the properties of the media in which planes, boats, and other things float or fly, aspects that we can't see with our eyes, are what govern their movements. Whereas thermodynamics describes the relationship between heat and the forces that allow it to be transformed into work, fluid mechanics describes the relationship between pressure, mass, and the flow of fluids. The laws of thermodynamics explain how our cells turn food into fuel, but the principles of fluid mechanics govern how our blood flows throughout our bodies and how our internal plumbing system functions and sometimes fails. Over the next 2 lectures, we're going to explore these principles and how they govern everything from the pain in your ears when you dive to the bottom of a pool to the sometimes bumpy experience of air travel. You might be thinking, if we're going to talk about fluids, why are we discussing airplanes? Planes aren't boats, planes fly in the air, they don't float or move through water, and air is a gas, right? That's true, but when we talk about fluids, we are referring to any material that can flow, and that includes both liquids and gases. These materials differ in their respective states, which we intuitively recognize as the difference in their mass density. Simply put, mass density is the mass per unit of volume, or how many molecules are stuffed into a specified area of space. Air has a low mass density because its molecules of oxygen, carbon, and so on are spread widely apart, while water, or say the liquid mercury in an old thermometer, have a much higher mass density as their molecules are tightly packed. And solids, of course, have the greatest mass density of all. Let's think about mass density by imagining a New York City subway car. The subway car is the specified area that we're talking about. Now, if it has a low mass density like that of air, that's just 2 or 3 people in the car. A high mass density like motor oil, that's a crowd of people with every seat taken and a few standing up. And the mass density of a solid, much higher than those of gases and liquids. A hard substance like a diamond, that's a jam-packed subway car full of passengers, luggage, and maybe even some chickens and goats thrown in with no room for anyone to move. I opened the lecture by telling you that fluid mechanics is about pressure and mass. But what do we mean by pressure? What's pressing on what? We have to be precise. So let's think of pressure as the force acting directly on a surface. That is, force exerted at an angle perpendicular to the plane of the surface. You can visualize this like the letter T on its side, with the short line of the T representing the surface and the long line of the T representing the force impacting directly upon it. Technically speaking, pressure is the magnitude of the force per unit area. Pressure is a useful force to understand. It's around us all the time, as in the air pressure of the atmosphere. Walking around on land, we're at the bottom of the Earth's atmosphere, which extends from the ground to the stratosphere. We hardly notice the air pressure around us, but it's easy to observe. For instance, consider a vacuum-sealed object in a bag, such as one of those bags of ground coffee that sometimes look like compressed bricks. They look that way because the vacuum process extracts the molecules of air from inside the bag, thus greatly reducing the internal pressure. The external pressure now becomes quite high by comparison, so the bag crumples inward, creating the compact, shriveled look that you're familiar with. So, despite what it might seem, vacuum packing isn't a process of pulling the sides of the bag in, which you might think is happening considering the physical sensations of airflow that we feel when we put our fingers in front of a vacuum nozzle that's doing its job. Instead, The appearance of vacuum packing is due to the external air pressure pushing from outside, pushing the bag in and compressing it. In order to understand how planes fly, we need to get familiar with the forces and the relationships between them that underlie the physics of flight. So let's add another concept to our toolbox. Pressure in a static environment, specifically the relationship between pressure and depth. In general, as vertical depth increases, in other words, as you go downward into a fluid, you swim down to the bottom of the pool, fluid pressure also increases since the lower layers are compressed by the weight of the upper layers. I don't think this is a major revelation to you. Air is at a higher pressure at sea level than at the top of Mount Everest, the difference in vertical depth being the height of the mountain. Now, you might have heard that it's hard to breathe at the top of Mount Everest, but that's not because there's less oxygen up there. In fact, there's just as much oxygen as anywhere else in terms of the proportion of oxygen in relation to all the other molecules in air. 21% of air molecules are oxygen, whether you're at sea level or at the summit of Mount Everest. But the air pressure is much lower at high altitudes than we're used to. The molecules are further apart from each other, even though the proportions are the same. A few years ago, I went on what was one of the best vacations of my life. My husband and I trekked to the base camp of Mount Everest in Nepal, reaching a final altitude of about 18,000 feet. That's 4,000 feet higher than the highest mountain in the continental US. That part of the Himalayas is breathtakingly beautiful, but the trek literally takes your breath away. The key to survival is to take it slow, allowing your lungs to accommodate to the change in altitude as you climb. Why is that necessary if the amount of oxygen in the air doesn't change? Well, as the air pressure decreases, because you're higher up and there are fewer layers weighing it down, your body needs to work harder to extract the oxygen from the air. Now, your lungs work by creating a pressure differential between the air in your chest and the air outside of your nose and mouth. Nature abhors a vacuum. So when the pressure in your lungs is lower than the pressure outside, air rushes into your nose and mouth and down into your lungs, where a vast network of capillaries can extract oxygen from it. But when the pressure outside is lower, less than that of the air in your lungs, less of the air makes it into the lungs, and therefore there is less net oxygen and other air molecules traveling through your bloodstream. At the top of Mount Everest, where there is very little air pressure, your lungs and your bloodstream need to work very hard to get any oxygen at all. And, in fact, you are oxygen deprived at the summit. The sad thing is that this oxygen deprivation has very real effects on our bodies, especially our brains. It's a little known fact that many professional mountain climbers who spend a lot of time at high altitude often develop dementia and other cognitive symptoms of chronic oxygen deprivation later in life. But if you haven't experienced the shortness of breath, headaches, and other symptoms of altitude sickness, you've probably felt the pain in your ears as you swam to the bottom of the deep end of a swimming pool. The fluid pressure at the bottom of the pool is higher than that at the surface, again, because there's more water weighing it down, and we can easily feel that pressure increase as the painful push on the outside of our eardrums as we descend. But there are some subtle yet important implications of this observation. If you stand up right now, the blood around your heart will be at a higher vertical distance from the floor than the blood at your feet. Now, ignore for a moment that your blood is moving. It is absolutely true that the blood pressure in your lower legs is higher than it is in the aorta of the heart. Feeling lightheaded? I often do now that I'm almost 7 months pregnant, and much of my blood is being used to feed my baby. But that pressure can be equalized simply by lying down. And that increased pressure in your legs, if you've been sitting or standing still for a while, is what can cause a life-threatening blood clot called deep vein thrombosis, or DVT for short. If you've been sitting for a long time, say on an overseas flight, you can develop a clot or a coagulation of blood in a vein in one of your legs, which can be life-threatening if it travels to your lungs, heart, or brain. That's why, to avoid DVT, doctors recommend getting up and moving around every hour or so on long flights to ease up on the pressure of pooling blood in your legs. I'm sure you've already made the connection that the change in pressure swimming to the bottom of the pool is much greater, even with just a few feet of descent, than is the change in pressure when hiking to the top of a mountain from sea level, which could be hundreds or even thousands of feet. The difference, of course, is the density of the fluid surrounding us. Static fluid with a higher mass density will accrue a larger pressure difference as the vertical depth increases. So if we think about our New York subway car again, going deeper in a high mass density fluid, like mercury for example, is like stacking crowded New York City subway cars on top of each other, creating a higher and higher pressure environment below them. Now, stacking empty subway cars will create less pressure below them by comparison, as is the case with liquids and gases. There are many ingenious ways that we can put fluid pressures to work for us. Let's go back to the deep end of the pool that we talked about a few minutes ago. Why do some objects float and others sink in that pool? If you said density, you're part of the way there. Yes, indeed, water has a mass density, and yes, ice has a mass density that is lower than that of water, and so the ice floats. Remember, we talked about this property of water that makes it possible for us to live on Earth back in the very first lecture. But what about the cruise ships in, say, the ports of Miami? What about the felled trees in the river? Certainly the mass densities of steel and wood are higher than that of water. Here is where a new concept comes in: buoyant force. Buoyant force is the force that all fluids apply to objects immersed in them. Objects in a fluid displace that fluid, so one can think of the buoyant force as an opposing, upward force exerted by the fluid back onto the object. Little kids with inflatable water wings on their upper arms will feel the power of buoyant force if they try to swim below the surface. They will literally feel the water pushing their air-laden bodies back to the top. As you might imagine, mass densities are important here. The Greek scientist Archimedes determined that the magnitude of the buoyant force equals the weight of the fluid the object displaces. This is known as Archimedes' principle. What do I mean by the weight of the displaced fluid? Now imagine I made a special coffee mug that had a circular trough around the rim. Now, I love my coffee, so I don't want to lose a single drop to spillage. And the trough around its circumference will catch any liquid that runs over the rim. Let's say I fill my special mug right to the very top with coffee. If I place a spoon in the mug, of course, some coffee will spill over the edge, but I've collected it in my trough. If I then went on and weighed that spilled coffee in the trough of my special mug, Archimedes' principle tells me that the weight of that volume of coffee which was displaced by the spoon would equal the buoyant force the coffee in the mug is exerting on the spoon. It's not much, and the force of gravity acting on the spoon greatly exceeds it because of the spoon's much higher mass density, which is why the spoon doesn't float. The spoon in the coffee mug example illustrates an important point. For objects that are solid throughout, whether or not that object will float depends only on its density relative to the density of water and the maximum buoyant force that water can exert. Being solid is the important factor here. The steel that makes up a cruise ship will not itself float in water, but steel as a part of a mixed material object like a cruise ship can be made to float. The addition of other materials, like all the air within the ship's hull, means the buoyant force created by the huge volume of water displaced by the massive ship can and hopefully will be sufficient to balance the ship's weight, which of course is considerably less than it would be if it was only made of solid steel. Therefore, it floats. But how do we get that massive ship moving? To this point, we've discussed basic properties of static fluids only. But air and water aren't always static. So to understand how planes fly through the air and ships cross the oceans, we need to consider what happens to fluids when they're moving. And to do this, we need to understand Bernoulli's equation. Bernoulli's equation is an elegant mathematical formula that explains the relationship between pressure, fluid density, and fluid flow rate. It applies to everything from airplane wings to throwing a curveball to configuring the plumbing in your house. Understanding this equation will enable us to understand why planes fly, ships float, and the curveball can strike out the best batters in baseball. Let's start with how fluids actually move. Intuitively, we know that the flow of fluids can be steady or unsteady. That is, calm and smooth, like water down a water slide, or choppy and turbulent, like the whitewater rapids on the Colorado River. And just like water in a churning ocean or a still lake, air can be smooth or turbulent. The physical properties of these different types of flow can be defined by the constancy or uniformity in the velocity of the fluid particles crossing a particular point in space. Now imagine that you're a rock at the bottom of a river, sensing the movement of the water around you. In perfectly steady flow, you would feel that all particles pass at the same constant velocity. Unsteady flow is, of course, different. In unsteady flow, you would feel the velocity of the fluid particles change over time. Again, think of the choppy water on a river rafting trip, with the water flow changing speeds and direction many times. In your rock state, you might feel that some of the water coming at you flows quickly, but as it breaks on your surface, the water flowing downstream from you might be traveling more slowly. So that's flow movement. It can be steady or it can be unsteady. But in addition to the steadiness or choppiness of fluid motion, different fluid substances can also be more or less compressed. Liquids and gases differ in their compressibility. The mass density of liquids is fairly constant despite pressure changes. That is, the density of water is the same at the bottom of the pool as it is at the surface. That is, the number of molecules of water in a given amount of space or volume is the same whether you're at the surface or down in the depths. But remember that the pressure is higher at the bottom because there's more matter pushing down on an object at the bottom of a pool than at its surface. We feel this pressure in our eardrums as we dive to the bottom. Our eardrums can be squished by the pressure of the water, but the density or the number of molecules per cube of water remains the same. Gases are different, however. They can be compressed. That is, one can pack more and more molecules into an area. Tanks of oxygen are compressed this way, and that's why at the top of Mount Everest, tanks of oxygen are used to deliver more air to your lungs. Artificially, they have a higher pressure than the air at the summit, making it easier for your lungs to get the oxygen into your bloodstream. So, fluids can differ in terms of how they move and how much they can be compressed. They can also differ in terms of how they flow. Viscosity refers to how easily a fluid flows. We can think of viscosity like a measure of thickness. It's obvious that honey is thicker than water, and it flows more slowly and less easily than water. So honey has a higher viscosity than water. Now, to understand fluid mechanics, we need to imagine what it would be like if we had an ideal fluid. An ideal fluid is an incompressible, non-viscous fluid. It doesn't exist in the real world, but it's a useful construct for some thought experiments we're about to engage in. We discussed mass density earlier in the lecture. In a flowing material, we can appreciate that all those molecules in space which are making up the density are moving and therefore creating a mass flow rate. Water through a hose has a mass flow rate which we observe as the water molecules streaming out the open end over time. Faster flowing water has a higher mass flow rate than does slowly flowing water. But here's a concept to remember. Assuming that a closed system is what we're talking about, that is, no other forces can act on it, the mass flow rate at the entry point must equal the mass flow rate at the exit point. So back to our hose. Assuming there are no holes in our hose, making it a closed system, the flow rate of the water entering the hose must be the same as the flow rate of the water that exits the hose. This is known as the equation of continuity, and it explains why it helps to put your thumb over the end of a running garden hose to increase the speed of the spray of the water when you water your lawn. Your thumb partially obstructs the end of the hose, forcing the water to exit more quickly in order to maintain the same mass flow rate across the entry and exit points. The equation of continuity explains that the water seeks to conserve the amount of flow, so it must do so by forcing more water out of a smaller hole. It also helps to explain why changing your shower head to one with smaller holes can enhance the flow of water falling on your head, but not, of course, the volume of water that you're using. We now have what we need to understand Bernoulli's equation, a fundamental concept in fluid dynamics, and one that I'm sure you will come to love as much as I do. Bernoulli's equation is named after 18th century physicist Daniel Bernoulli, and it describes the relationship between pressure and two other factors, speed and elevation for steady flow of an ideal fluid. For example, his equation predicts that for a flowing fluid at a constant elevation, like water through a horizontal pipe, the fluid pressure will decrease as the flow rate increases. His equation also predicts that for flowing fluid at a constant speed, the fluid pressure will decrease as elevation increases. Why are these assertions true? What would make the flow rate increase under horizontal conditions? First, remember that pressure is the force exerted per unit area. As the mass flow rate increases, pressure decreases because those fluid molecules are less able to exert their force perpendicularly onto their surroundings. They're moving too fast to push on the walls of the pipe or whatever it is that's holding them. Think again about the equation of continuity. If we connect a large diameter pipe to a small diameter pipe and move water through it in a horizontal position, we would find that the flow rate increases and fluid pressure decreases as the water moves from the large to the small diameter pipes. This is counterintuitive. You might think that as flow rate increases, so too does pressure. But the opposite is true. And this feature of fluid motion is what allows airplanes to fly. To imagine this, think about a truck at a stop sign with a tarpaulin above the truck bed. Now, at rest, the tarpaulin is flat. The pressure of the air above it is pushing it down. But as the truck starts to move into the intersection, the tarpaulin begins to lift up. That's because the pressure of the air molecules pushing down on it is decreasing as the air molecules move across the top of the truck more quickly. We learned earlier in our discussion of static fluids that depth affects pressure, namely that increasing the depth within a static fluid increases the pressure. Bernoulli's equation accounts for this as well within its description of fluids in motion. Specifically, Bernoulli noted that as the elevation of fluid increased, the pressure decreased. So if you imagine a pipe of constant diameter with an uphill trajectory, a pressure gauge would read a lower pressure at an uphill point than at a downhill point for fluid moving at a constant flow rate. So Bernoulli's equation describes the relationship of fluid pressure with fluid flow rate and with fluid elevation or depth. At a constant elevation, as the flow rate increases, pressure decreases. At a constant flow rate, as the elevation increases, pressure decreases. Now it's time to put Bernoulli to work. The physics of airplanes depends on Bernoulli's equation. An airplane wing is shaped such that airflow, which is the fluid in this case, moves faster over the wing than it does under the wing. I love that the technical name for a wing's shape is airfoil, as if the wing is foiling the air's plans and splitting it up, like splitting up a party. The faster moving air over the wing in accordance with Bernoulli will result in a lower fluid pressure, or air pressure, than that under the wing, resulting in an imbalance between the two sides of the wing. The air pressure under the wing will now exert a greater force under the wing, producing a net upward lift. Extend the area of the wings enough and generate enough airflow over the wings, and the resulting lift will be sufficient to pull a massive aircraft into the sky. Lift is analogous to the buoyant force that we discussed earlier, which, when large enough, is sufficient to overcome the mass of an object so it floats. So lift needs to exceed the mass of the plane to allow it to take off and stay airborne. Let's talk about a health issue for a moment that brings in Bernoulli's equation too, and that's the impact of aneurysms on blood flow. Aneurysms are abnormal enlargements or bulges that can occur in the blood vessels of the circulatory system. They're vulnerable to rupturing, which can cause a stroke if the burst occurs, say, in the brain. At the point of the bulge, the cross-sectional area of the vessel increases. Bernoulli's equation tells us that the fluid pressure then will also increase, assuming that the person is lying down and therefore the elevation is constant. Fittingly, the equation of continuity tells us that the increase in cross-sectional area at the bulge means a decrease in the flow rate. Think taking your thumb off the end of the hose of your water hose, causing an increase in fluid pressure at that spot. So the principles of fluid dynamics explain the vulnerability and weakening of our blood vessels in this situation. So far, the principles of fluid mechanics have shown us how a plane is lifted into the air, why a ship floats in the ocean, and how the movement of fluid molecules in air and water allows these things to happen. But once a plane or a ship is moving, we need to steer it to a destination safely and accurately. Is flying in the sky just like driving along a road? What are the unique challenges of navigating through fluids rather than on the ground? It's not enough to just fly and float. We need to harness the atmosphere and the oceans to take us where we want to go. In the next lecture, we'll turn to navigating through fluids and discover how fluid mechanics gives us the tools to dominate air and sea, in addition to land.